Howdy, everyone. Happy Monday, and maybe not so happy multi exam week for many of you. The good news is you'll at least have a reprieve after this week in terms of having exams for a while. Uh, Finals, of course, come next. I think most of you realize why you get an interesting answer from this calculation, as somebody put in the chat. Message 259 times 39 is 10101. And so you just get your age several times. Now, if anyone in the class happens to be over 100 years old, then this unfortunately would get muddled up and not work, I assume. Okay, over the weekend, I sent you this figure, and I wanted to make sure that you are aware of how zero-point energies affect the E zeros when we're doing equilibrium calculations. So I could have drawn this a little bit prettier, but this is supposed to represent the potential energy curve for HF, for the vibration of HF, and this shows the anharmonicity tailing off at the dissociation energy. As we've seen before, if we go from the bottom of the potential energy curve up to the dotted line, the dissociation point, that's called D sub E. And that's 48,502 wave numbers. And HF has a vibrational frequency of 3959 wave numbers. And so its zero-point energy is very close to being 1/2 of that. And we can make that assumption. Its zero-point energy is 1930. The actual amount of energy it takes to dissociate HF is this 48,000 number minus the zero-point energy. Because it's got a head start, it's up 1930 wave numbers. So if I subtract 1930 from 48,000 something, I get 46,572. So I meant to draw an arrow all the way up, but from this solid line up to the dotted line, that's how much energy it takes to dissociate HF. But if we make the deuterated form of HF, so hydrogen of mass 2, its vibrational frequency drops to 2907 because its reduced mass is larger. And so its zero-point energy drops to 1454. So you see there's a difference of, 476 wave numbers between these. And so it's that much easier to dissociate the DF. Sorry, it's that much more difficult to dissociate the DF than the HF because it has to start from this lower dotted line. Well, what makes a difference is if you get an equilibrium problem, that's something like this. And there's some in the problem assignments, and I thought I'd assigned something to you from there, but apparently I didn't. But think about what I've written here. If we have HF plus DBR in equilibrium with DF and HBR, HF and DF have exactly the same potential curve. So they have exactly the same DE, but they have differences in D0 due to the zero-point energy. And similarly for HBR and deuterated HBR or DBR, they have different zero-point energies. So here are the vibrational frequencies. Here are the zero-point energies. If you have an equilibrium problem like this, then you have to use the zero-point energy differences to figure out the net difference on the two sides of the equation. So what you do is you take delta E0 to be the sum of the zero-point energies on the right minus those on the left. And in this case, you get minus 116. So if you have an equilibrium problem, that exponential term, e to the minus delta E0 over kt, this is the value that you would put in there. And since it's minus here, then that would become positive. And I'll go over the review sheet. Somebody says, should APE of HBF be 1980 or ZPE? Did I make a mistake? Yes, it should be 1980, my mistake. So there's a math error. And as I promised you, I always make mistakes on my exams and things like that. Okay, incidentally, then again, the exam is Wednesday. When I was working out the answers, I concluded that it's actually a fairly difficult calculations intensive exam. So try to have gone through some of these calculations several times so you can do them smoothly when you get the exam. The exam was also somewhat harder and longer than I thought, so I actually modified a couple of the problems to make it more manageable. But it's going to be a fairly challenging exam in terms of having to do calculations. Okay, another chat comment. The error on this page was I didn't know how to take half of 3959, and I wrote 1930. That would have been half of 3860, but it should have been 1980 right here. And then the mistake follows through here. It should be 1980 here on the minus sign, and wind up with minus 166. Okay, well, let's go back to the exam review. And so there will be some concept questions. I think there are 3 multiple choice questions and others related to some of this stuff in a similar way. Another chat question. ZPE is 0 point energy. So half of the vibrational frequency is the 0 point energy. Okay, so you've heard that I think I'm really impressed by Boltzmann's ability to come up with all this. And basically where he started from were some logical conclusions. We have a fixed number of molecules. If you add up the populations of all the quantum states, it'll be the total number of molecules. And then if you want to know the total energy, if you add up the energy contribution from each state, which is the number of molecules times the energy of that state, you'll get the total energies. And we can take derivatives of those. And since capital N and capital E are fixed, the derivatives are 0, and we can write them in this form. And then we borrow this weight of a distribution formula from statistical mechanics, and that's really all we need from statistics. I said we borrow it from statistical mechanics, but we borrow it from statistics courses. And this is one of the things you've learned. And then Boltzmann comes along and he says, if I add 0 plus 0 plus 0, I can get 0. The first 0 he starts from is that we want the weight of the distribution of molecules over all the quantum states to be maximized. And we do this by setting d log w equal to 0. We could have done it with dw equal to 0, but when we go through the math, it turns out it's a lot easier to do this. Plus, this gives us manageable magnitudes, especially after we apply the Stirling approximation, which reduces these factorials into simpler form. Okay, so this is the Lagrangian approach of adding up a bunch of zeros. We use the Stirling approximation approach, and you're not going to be asked for the derivation of this, but I do want you to be aware of where all of this comes from. And when we get to the end, then we find that the ratio of molecules in one quantum state compared to all the molecules is given by this. So for any individual quantum state, its population is proportional to exponential to the minus e sub I over kt. And the denominator winds up looking like this, and this is what we call the molecular partition function. It has this formula, It is really a summation. Doesn't matter if we're talking about translations, rotations, vibrations, it's a summation. Uh, Later on, we make approximations. That summations can be uh, approximated by integrals, but in reality, this is always the definition as a summation. I don't know if I have it in the review notes, but we always assume that the lowest energy we can work from, whether it has a 0 point energy or not, is energy 0. So the first term is e to the minus 0 over kt, and that, of course, is 1. So the summation always will be 1.0 plus a bunch of other terms. And so you can never get less than 1.0 for the partition function. Okay, so this is basically the ratio of molecules as compared to all of the molecules. Now, I should point out that if you go to something like vibrational levels, and the vibrational frequency is quite high, this can be approximated, or not even approximated, well represented by n sub I over n0 is equal to this. In other words, 99.99% of the molecules may exist in the lowest state, and then you can just say n sub I to n0 is the same as n sub I to the entire number of molecules. I may have something about that a little bit later. Okay, well, once we have Q, then this is one of several important equations that you'll be asked to apply on the examination. Internal energy is minus the number of molecules over the partition function, then times dq d beta. So one of several important equations. So from this equation, this is basically the internal energy, which is often represented as E minus U naught. Then perhaps the hardest part about statistical mechanics to understand is the concept of ensembles. And we had to do this to say that we are allowed to have small fluctuations in energy between very, very similar components of this ensemble. And if we're allowed to have some fluctuations, then we're possible to have the entropy. We still make sure we keep the entire energy constant and the number of molecules constant, but this is a way of coming up with the canonical partition function, which we can then relate to the entropy. Okay, the next very important equation is this one. Capital Q is the molecular partition function to the nth power over n factorial. Capital N always is the total number of molecules. Your notes mention that this is the second form is what you'd have for distinguishable particles, but we're always going to work with indistinguishable. And here we've said it's a typical case. It's almost always the case. One relationship you may or may not have seen before, but it's useful and you want to keep in mind: number of molecules times the Boltzmann constant is equal to the number of moles times the ideal gas constants. And notice then, if we put in 1 mole here, then capital N would have to be Avogadro's number. So Avogadro's number times K is equal to the ideal gas constant. Okay, so at this point, hopefully we're convinced that finding little q and capital Q are important for calculating the thermodynamic properties. So we need to go through translational, rotational, and vibrational types of partition functions and multiply them together to get our complete molecular partition function. We can also after we go through this, find that we can write the internal energy in terms of a partial derivative with respect to the log of the canonical partition function. But as I've said in class, I strongly recommend using this form. It's still a lot easier for the internal energy than going to finding capital Q. capital Q can be rather a pain in the neck to have to calculate. Okay, then I presented the Boltzmann formula, and then I rationalized where this came from. This is considered one of the great scientific laws of all time by many people. And after we came up with this, we saw that we could write the entropy according to this. So internal energy divided by the temperature plus the Boltzmann constant times the natural log of Q. When you have to evaluate this, notice again that this is the form of capital Q. We're going to want the log of Q, and so we're going to wind up with the log of n factorial as part of the solution. And so we're going to have to resort again to using the Stirling approximation for this. So make sure you're aware of the individual steps that you need to do. I think in the super problem, we worked this out. You do need to be careful that the method I've suggested for calculating log of Q and calculating the first term, you're going to get the first term in terms of contribution per mole, and the second term would be the absolute total entropy for the number of molecules that you have. So check the practice calculations on that. Okay, the next part I'll just kind of brush over. I showed you that all the other thermodynamic functions could come from the internal energy and entropy. Of particular interest, I always find, is the Helmholtz function, which is given like this. And there's a formula, which I had not known before I started teaching this course, that you can find the pressure in terms of the derivative of the Helmholtz function with respect to the volume. And if we apply that formula, we derive the ideal gas law. Someone either emailed or texted me and asked me whether the ideal gas law came from statistical mechanics, and the answer is no, it was known before that. Notice that NR, the number of moles times the ideal gas constant, is equal to capital NK. So the Boltzmann constant would not have been known at that time. They were simply using the number of moles in capital R. Okay, so what we needed was we needed to find the individual components of the partition function. The three-dimensional particle in a box problem leads us to finding the translational partition function, and we can always write this as tau times volume. And as I promised you, I would tell you what this constant is, excluding the m and t parts, which can be variable. And it's, I think, 1.88 times 10 to the 20th. In my notes, at least in one place, I have the units for tau incorrect. Tau should be in centimeters to the -3. And so you have to put your volume in cubic centimeters. I will have the correct units on the cover of your third examination. Okay, for rotational levels, the best way to find these is by direct summation. If we have a diatomic molecule, then you'd sum up a lot of terms like this. You start from J equal to 0, the lowest state. Then you put in your different energies, you calculate the contributions. In the super problem that's in your lecture notes, we do this summation for several of the terms of, the carbon disulfide molecule that we had there. So make sure you're able to do this by direct summation for at least a few of these terms. You can also do this calculation based on an integration approximation. So if you turn this summation sign into an integral and see what the integral comes out to be, this is the result that you get, that the rotational partition functions are kT, and the bar means in wave number units, divided by the rotational constant. And then if the two atoms are different, then you don't have to divide by anything. But if they're the same, like they would be for N2 or O2 molecules, then you put a 2 in the denominator. I've often told you that KT at 25 degrees centigrade is 207.2 wave numbers. And I've also suggested that if you have to go to other temperatures, take the ratio of the temperatures and multiply it times 207. So if you're at 100 degrees centigrade, that's 373 degrees Kelvin. 373 over 298 times 207 will give you the KT at 100 degrees centigrade. The rotational constant would be given for this exam. For the second exam, maybe you had to calculate it from a spectrum or such, and possibly you might have to calculate it again on the final, but you'd be given any information like that you need. Vibrational frequencies you'd also be given. Now, comment about this approximation. This works if the energy levels are close together. And so this says the approximation works very well unless B is large. And so if you have light molecules and you have large B values, like for HCl or HF or something like that, then it probably wouldn't work very well. You can still do the calculation, but you might get a number that's not nearly as good as direct summation. In the review here, I'm giving you the equation that you would use for polyatomic molecules, but I'm not going to give you a problem for that. For the vibrational part, for each frequency that you have for a molecule, you use this formula right here. The bars indicate, again, that we want these in wave number units. Notice that this is e to the minus nu in the denominator. So if nu bar over kt gets to be very large, let's say we have e to the minus 5, it would be 1 over e to the 5th power, and that basically goes to 0. So if you have a vibrational frequency that's much higher than kt, say 4 or 5 times higher or more, then you don't even have to worry about this calculation. You just know it's going to come out equal to 1.0 as the contribution. Electronic states, the contribution is almost always 1 unless you have some unexpected degeneracies. And as I've said before, no Q component is ever less than 1.0, since the first term will always give you e to the minus 0 equal to 1. Okay, then we went excuse me, through the process of average energies. I took that formula that we had, capital N over Q dQ d beta, and I looked at what you would get for each of these components, translational, rotational, and so on. For translations and rotations, the average energy per molecule is very simple. You just need to know for translations, it's 3/2 kT. For rotations, it is kT for a linear molecule, or 3/2 kT at higher temperatures. Here I've written that the actual function is 0 at absolute temperature of 0, but once you get to about 50 degrees Kelvin, then you can just use these approximations. And why do we have 3/2 here and 2/2 here and 3/2 there? There are 3 degrees of freedom for translations. We can have translations in X, Y, or Z directions. For rotations, diatomic molecules have only 2 rotations, so 2 times 1/2 kT. But polyatomic molecules that are not linear will have 1/2 kT per rotation, so we have 3/2 kT. So that's what the equipartition principle is about. And again, this goes way back, well before Boltzmann, and probably instead of using K's here, they used R for the ideal gas constant, since we have the relationship between K and R. Okay, so we don't need to say anything more about the equipartition principles, but you can see where the 3/2 comes from for translation and rotation. Just ignore it for vibrations. It almost never works. It only works if you have very low vibrational frequencies. You do need to use a separate formula for the vibrational average energy. And so this is one that you might want to write on a separate piece of paper. It'd be one you might need to use. So you can calculate your vibrational average energy from this expression right here. And the answer will come out to be in wave numbers, centimeters to the -1. So when you're done calculating the total average energy per molecule, you basically need 3/2 from the translations. Most molecules will have 3/2 for the rotations. And you know that KT is 207.2 at 25 degrees centigrade. So you can easily calculate the total average energy of these two in wave number units. And on the cover sheet of your exam, I'll give you a conversion from wave number units to kilojoules, just in case you have a question needing to relate that. We talked briefly about heat capacities. They basically work out the same way. We have 3/2 number of moles times R for translations, 3/2 NR for most molecules, for rotations, only NR for diatomics. But then for vibrational cases, it gets to be more complicated and you actually have to work out the mathematics for it. But once you know the relationship for the overall energy, the heat capacity is just the derivative of energy with respect to constant volume. You can get it from that. But you won't be quizzed about that. I went through a sloppy calculation for total heat capacity for water. Textbooks like to show it, but as I said, this last term is rather flaky because it's very hard to know what is an active vibration. It's not a black or white question. It's how many vibrations are not much higher in energy than KT that will contribute. So this will always be some kind of fudge factor number that you get in here. So this is not a particularly useful formula. And we have a chat question. What equation do we use for the average energy? It is right here. So for the rotations and translations, you just have the 3/2 KTs or 2/2 KTs. For the vibrational energy, you have to use this one. And then put them all into wave number units and then convert with a conversion factor to kilojoules, and you'll have that. The conversion factor automatically takes you to the energy per mole. So if you're asked for total energy, you have to multiply the number of moles, which most likely you'd have to calculate from the ideal gas law. Okay, and I did put an equilibrium constant problem on the exam. And so we went through the rationale for the results that we got. And the rationale was that we're going to have a delta E0 between molecules on the left and molecules on the right. So look at this diagram carefully and think about what we talked about when we talked about the 0-point energies for isotopically substituted molecules. So when I talked about HF and DF, they were at different energies and they were on different sides of the equilibrium expression. So one of them, namely the DF, would have had the lower energies because its 0 point energy was less than for HF. And so the delta E0 from DF going to HF would be this expression right here. Okay, another chat question. What is the conversion factor between wave numbers and kilojoules per mole? It'll be on the cover sheet of your exam. What I remember is 350 wave numbers is 1 kilocalorie per mole. And so I think it's 83 wave numbers per kilojoule. So if you get an answer in wave numbers, you would need to divide by about 83. Okay, 11.96 joules per mole. That's per wave number, I guess. But notice this is in joules, since we're usually talking about kilojoules, then that's where this 83 comes from. So if you take the reciprocal of this, you'll get something like 8.3 times something. But it'll be on the cover sheet of your exam. Okay, so we went through a bunch of this rationale, and our conclusion was that if we're going to have a equilibrium with molecules on both sides of the equation, we have to calculate the partition functions of the molecules on the right-hand side, multiply them together, divide by the partition functions of the molecules on the left-hand side, and then we take this e to the minus delta E naught over kT. And this E naught basically the E naughts are the dissociation energies of the molecules on the right-hand side minus those on the left-hand side. So I've noted here E naughts include both chemical energy terms and 0-point energy terms. Look at the attachment that I sent you over the weekend and we discussed first today. That'll show you how to deal with it if our chemical energy terms are the same. So if we have HF on the left and DF on the right, then the chemical energy terms are the same and the total E naughts only come from the 0-point energy change. So that's pretty subtle, but if you look at the attachment I sent to you, hopefully that'll be easier to understand. Okay, so I think that completes the review. And so I'll go back to our lecture notes, which I need to stop the share. And find what I want. So I apologize for the delay. Okay, so last time we talked about the super problem. I'm now just scrolling down and about to share the screen with you um, for the other practice problem. Um, okay, so finally, sorry about that. Uh, Last time we briefly got started talking about this particular problem. First, I have a couple chat questions. Question, the exam also covers electronic spectroscopy. What should we study or review for that topic? Um, it'll have a couple of concept questions related to the electronic spectroscopy part. We talked about fluorescence, phosphorescence, lasers, and also just the nature of electronic excited states. We have transitions from lower bonding molecular orbitals to higher bonding molecular orbitals. Usually we get more anti-bonding character in the excited state, so bonds get weaker and bonds get longer. So in the second exam review that I sent you several weeks ago, it had a section on electronic spectroscopy. So I suggest you look at that. There won't be any problems, but just look at things in your lecture notes for concept questions. And someone else is asking, can I emphasize again what we should focus on? You're going to have questions related to internal energy. You're going to have questions related to entropy. You're going to have an equilibrium question, which will have those components in there. And that'll be about half of the exam. You'll be needing to calculate molecular partition functions, and that means translational, rotational, vibrational, and electronic parts. You'll need to calculate internal energies. So we have these formulas, 3/2 kT as the average energy per molecule for translation, for example. And if you know the average energy per molecule and you know the number of molecules, then of course you can calculate total energy. And then you'll have a equilibrium problem, something of this type. Okay, here's another case where I have a mistake in my units. So when this is 10 to the 20th, this should not be meters to the -3. This is centimeters to the -3. So I may have worked this out wrong. It turns out a book that we used to use had this mistake in it. And so sometimes I have it correct in my notes, and sometimes I don't. But I'm making sure I have the correct units on the our exam that we have. And it'll look just like this. It'll be centimeters to the -3. Okay, so typical problem here. We may need rotational constants to calculate the rotational partition functions. And we may need vibrational frequencies to calculate vibrational components. In this particular problem, you'll notice the vibrational frequencies are all very high. The lowest of these is still 8 times higher than kT. So without even having to do a calculation, we can realize that the vibrational partition function is just going to be 1.0. If we applied the formula to all of these frequencies as such, you might get the result that it's 1.00002 or something like that. Okay, anyway, in a problem of this type, this is exactly what you might expect to be asked for. Certain Q values for some of the molecules or one of the molecules, internal energy and entropy, and perhaps at different temperatures. For this particular problem, I tell you exactly what the E naughts are, so you know just to take the values for the molecules on the right-hand side of the equation, add them together, and then subtract the ones that are for the left side. Notice that all of these are minus signs. That basically means that we have very stable molecules. When they're formed, that much energy is actually released. Also notice that I don't give you an E naught value for the hydrogen atom here. So there obviously is no formation energy or dissociation energy for a single atom. So that value doesn't have to be considered. Okay, so here's a reminder of how we do things. You need to remember the total partition function has all of these components. Almost always QE is equal to 1. Then here I assume I must have probably done this incorrectly. I should have put in 1,000 for the volume as 1,000 centimeters cubed, since this formula will have tau in centimeters to the -3. So the answer on this problem set may be wrong, but the methods are correct. As always on your exam, you can get a lot of credit on your exams if you make numerical mistakes, but you show that you know how to do the problems. So I typically make math mistakes, but I would probably still get A's on my exams just by setting them up correctly. Okay, so if we take this formula here and we take our temperature at either 298 or 1273, the first case we take it at 298, and so QT is always going to be equal to this term times 298 times the mass to the 3/2. And then you can just read the masses off for the molecules. OH is 17, oxygen is mass 16, hydrogen is 1. So you multiply by 17. You don't need to convert to grams or anything because the conversion factor has already done that for you. Okay, well, obviously you get different QT values depending on the different masses that these molecules have. Hydrogen atoms also have a mass, so they're going to have a translational partition function. At 1,000 degrees, as you expect, everything goes up by roughly a factor of 1 when you do this. Sorry, 10 to the first or 10. Rotational partition functions, if you get a problem like this, that there's too many quantum states to add up for most of the molecules. So in these cases, one would use the approximation formula, KT divided by the rotational constant, and then divided by sigma if you need to. If the two atoms are different, sigma is 1. If the two atoms are the same, you divide by 2. So here are the rotational contributions. Again, notice the relative magnitudes of these things. The translational parts are humongous. Rotationals can still be substantial. For hydrogen, it's very small because it's got a huge rotational constant, 60.8. HCl, remember, is 10. I think we looked at carbon monoxide, and that was on the order of 1 wave number or something like that. So a huge rotational constant will give you a relatively low contribution for the partition function. 1,000 degrees, these numbers go up as you expect. In this particular problem, I did the calculation for the polyatomic case. And so I did all the substitution of the individual rotational constants here. And you see you get much larger values when you get into polyatomic molecules. If you try direct summation, now be sure that this is the kind of thing you can do. You're going to have a question like this. And I recommend setting it up exactly this way. You want to sum up these terms right here. So you put in your J, calculate 2J plus 1, calculate your energy, then you can calculate your exponential term, and then you get your contribution. If energy is 0, the exponential term is just 1, and 1 times 1 is 1. If the energy is 37.7 and you're at 25 degrees, it's 37 divided by 207. In the exponent, you get this value multiplied by 3. So you need to sum some of these terms together. I have some chat questions. Why does H2O have 3 rotational constants? You would know if you had studied for the second exam. It has 3 axes of rotations. All non-linear molecules have 3 rotational axes, and you can have a rotational constant about each of these. Linear molecules only have 2 rotations, and so they only wind up contributing KT and so on. Okay, so we're almost out of time, but be able to do this kind of summation. Okay, so you'll see I summed this up down to where we got to be 0.005, and this is a better value than using that approximation formula, but only a 4% difference is not very bad, and it works okay because oxygen is getting to be a somewhat heavier atom for this particular case. Okay, and here then the vibrational contributions for the hydroxyl radical. It's always 1 over 1 minus e to the minus frequency over kT. So as I've said many times, if the vibrational frequency is very much higher than kT, you're not going to get any significant contribution to the vibrational partition function. So you can quickly see why each of these go to 1.0. This exponential term essentially goes to 0. For water, all of the vibrational frequencies at 25 degrees centigrade are much higher than kT, so they all contribute to 1. But if you go to 1,000 degrees, you'll notice the angle bending vibration, which is at minus, well, it's at 1595 wave numbers. You wind up with an e to the minus 2 here, and so you get 1.20. So you start getting a contribution at a very high temperature. But note again, the key to it is what is the ratio between the vibrational frequency and kT. When it's only 2, it contributes. When it's 3, contributes a little bit, but when you're to 4 or 5, then you can assume that it's just going to come out to be about 1. So here's a ratio of about 4, and you can see at 4 you're getting a very, very slight contribution, but if you just wrote it off and say it's 1.0, it's not going to be a big error. Okay, so then you get your total partition function, you multiply the relevant parts together, and you get all these numbers. And again, do it at high temperature. Your equilibrium constant then is this. It's the Q for the components on the right multiplied together, divided by the Q for the components on the left, multiplied together, and then times this e to the minus delta E naught. And in this case, I gave you all the E naught, so it's a matter of summing these together. And when we get done with the problem, it's actually a rather boring problem because the reaction very much wants to go to the right. And so for all practical purposes, all the molecules are going to be on the right side of the equilibrium. However, and this is the thing to note, when we go to 1,000 degrees, we're going to start occupying a lot of higher quantum vibrational states. And this changes the mix of what you get. And the result of that is that this is still a very much favored to the right-hand side, but it's much smaller. So in a way, it's kind of a dumb problem because there's almost no equilibrium. On the other hand, it does show you what statistical mechanics can tell you when you have to go to higher temperatures. So I could have had a better example if I picked some different molecules. So we might have gone for a case where it was 10 to the third up here down to 10 to the first. And I think might have been quite a lot more interesting. Okay, so review both those practice problems a lot. And I think that's the key to doing well on Wednesday. And I expect it to be a hard exam, so if you breeze through it, you've done well. If you struggle with some of the problems, you might still get a very good score, because I think the grades may be kind of on the low side for it. But there will be a lot of calculations with those formulas, and so just be aware of how to use a lot of those. I'm not seeing any more chat questions, but I do now. Someone asked, how do you know when to stop after the direct summation? I will tell you when to stop. We don't have time during an exam period to have you do the full calculation. So I'll ask you what it is after 2 or 3 terms. So that'll be enough. And then someone else asked, how will we know if you made it into the top 15% of the class? That's pretty much up to the graders. And I will encourage them to grade quickly, but I'm quite sure they won't be done by Friday. So probably sometime over the weekend, we will know. Okay, so take care. And the exam will be done the same way as we have before. It'll be on eCampus, and I will also send you a copy. Make sure you answer your problems clearly and in order and stuff. Make it easier for the graders. It'll help you get a better grade. Take care.
Dr. Long.
Was that a question?
Yeah, I have a quick question. In the case of H2O, the sigma value is 2. So if we were given a molecule that wasn't diatomic, would you provide us with the sigma value?
I'll only expect you to know the sigma value if it's a diatomic molecule.
Okay.
So if the 2 atoms are the same, it's a 2. If they're different, so on.
And then I have one last question. Sorry. If a vibrational frequency is doubly degenerate, would you let us know, or?
Yeah. But I mean, you're not going to have any double degeneracies for diatomic molecules, for example. They only have 1 vibration each.
Right. Okay. Thank you.
I have another question. Why is there no rotational Q for H? Okay, somebody says because it's not diatomic. It doesn't rotate, so you have to have a bond before a molecule can rotate. So you have to have at least 2 atoms to rotate. Spinning around its own nucleus doesn't count as a rotation. Someone else says, for their super problem, will the molecule be similar or something we haven't seen before? Well, I've already put the super problem in your notes as carbon disulfide. Your exam will not have something called a super problem, but it will have an equilibrium problem. And it will probably have molecules that you have not dealt with before. Okay, everybody take care and see you Wednesday.